So this is my second to last talk. Depending on how today goes, I may switch gears a little bit tomorrow. So if you didn't, there'll maybe even be some pictures tomorrow. So if you hated everything so far, you can come tomorrow for something a little different. But we'll see. It depends on how fast I end up going today. And so maybe you should be happy if I don't get to it. But, all right. So so what I want to talk about now, where were we? When we last left our heroes, we were wondering how might we deal with this proving such an estimate, right? We had this estimate H equals Q inverse of some stuff projected down onto some low modes, right? And this was the span of the sigma k's, yeah? Right, and that was my QW. T was just the sum of sigma k w k t, yeah? So the sigma k's are my directions in the function space that I'm forcing, right? And this really is kind of an ellipticity statement, right? This is some statement about I have some quadratic matrix, which maybe I could call A of C, which is equal to summation C sigma k squared sum over k, yeah? And this matrix is non-degenerate on the range of pi, right? And that's so I can kind of kill things in the range of pi, right? And now what I want to do is I want to talk about how I might get such an estimate in a hypoelliptic setting, right? And remember what a hypoelliptic setting was, right? So my equation here generally has the form of Q dot plus BQ, write that correctly. And so I have these vector fields here, right? Which are these vector fields, yeah, right? And now if I'm going to get any new directions, it's because when I force here, they pass through this nonlinearity, right? This linear, if I think of these as being Fourier modes, then this can't help me at all because it's just diagonal. It's not going to make two modes interact. So I need to use this part of the equation to make things interact. All right, so to do that, I'm going to explain how you get this even in the fine dimensional setting for a second. I'm going to give you some indication of the ideas involved. And this was this at least goes, I mean, this was the idea of Maillevin to take this perspective on proving Hormander's theorem, right? Hormander's theorem, the celebrated theorem about hypoellipticity and propagation of kind of smoothing regularity of noise in systems using kind of the lower order part of the symbol. What I'm going to do now is I wrote this linearization. So what does this linearization say? This linearization, the odds are I would have come in and erased it and then redrawn the exact same picture. All right. So what am I going to do? I have this noise here, and I have direction sigma k that I can perturb the noise, right? These are the directions the noise are. And that's actually perturb in some direction. Okay, it's kind of a lie to say I perturb in some direction sigma k. I perturb in some basis direction ek, and q maps ek into sigma k. If this is time s, in the tangent space, I'm perturbing the equation in the direction sigma k, right? That's what this says right here. At each time t, I'm perturbing in these directions, yeah? And now, if I'm interested in the effect that it has on the equation on this random variable at time u of t, if I'm interested in what the effect of that perturbation has infinitesimally on this random variable here, what do? I flow that forward by going JST sigma k, yeah? Now what I have is I have this map from this Wiener process, right, into U of t omega, yeah? Map from C0t, if I only have finitely burning bounding motions, if I have m of them, Rm, into my function space, right? So I have vorticity, which is L2 of the torus plus divergence free and plus it's vorticity. So it is divergence free plus mean zero, okay? Know is what directions can I have, before I got lucky enough, this was a submersion. Remember what that is? It's a map that has a derivative, and that derivative is onto. So I want to look at all the directions that I can acquire in the tangent space at time t by wiggling a sigma k at some point in the path. What I just said was what I want to do is notice all the directions, see, that I can generate motion by wiggling in the direction sigma k at some point s in the past that affected at time t. I square it, make it positive. I integrate it up and collect all those directions. I collect, like you say, can you make motion in the direction c? Well, maybe I can. Let me check. The fact that I can make motion in the direction c is a statement about whether M is non-degenerate. If M is a quadratic form that only null space is the unit vector, is the zero vector, whose only null space is the zero vector, then M is not, and that implies a type of hyperellipticity. Okay, and that's what we're going to see now. All right. It doesn't map one-to-one onto Hormander's theory. It actually sometimes gives you results you couldn't get with Hormander, but it also, it gives everything you can. Well, I don't want to. Sorry, microlocal people. I didn't mean to say that. Go ahead.
How does so does each sigma k give you a different M?
Yes, because they're all independent Brownian motions. I can wiggle them all independently.
So you want to just check that at least one of these M's is non-degenerate for a given.
No, there's only one M. Oh, bananas. Typo. Right. Thank you for pointing that out. I didn't have a sigma k. That's why that sum is here. You might have been wondering why the sum was there. There's something going on in the back of the room. All right. So the thing you'd have to convince yourself of is that operator A that I wrote down before, M is actually AA star, where this is the adjoint. And at least this passes the first smell test. What did A do? A took a path, a variation, remember a derivative, and took you into a variation in the tangent space in Rn, in my target space. So A star takes you from the tangent space back to a path, and then A takes you back. So at least this is a quadratic object on the tangent space. First test, right? And it's positive definite, and this is manifestly positive definite, positive non-negative. Non-negative definite. Once you learn to speak French, you're wasted forever in English in this respect. Because in English, we can't decide which of our places we stole different words from to follow. And so whether positif means positive or whether positif means non-negative. All right, so formally, let's say that you can prove that this is non-degenerate. And let's say we're on a finite dimensional space. If it's non-degenerate, if M C equals 0 implies C equals 0, yeah? Right, that's what I mean by non-degenerate. Then it's in a finite dimensional space, it's also invertible. Because all topologies are the same thing, there's no space for anything else. So remember my game from before, if you remember back at the very beginning when I was proving the Euler-Lee formula, I wanted something like this, yeah? I wanted to find a noise variation that gave me that, right? Right? We solve things like this all the time when we teach, right? This is AX equals B, where this is B, and this is A, which is also A, and this is X, right? Yeah. And how do you do that? You find that if you're not sure about, like, if there's many solutions, like if this space is bigger than this, if this space is bigger than this space, right? There's a non-uniqueness of solution, so you usually choose the least square solution, the one that minimizes the L2 norm of this, which is really good because we already saw that the L2 norm of H is a thing we care about. So we're going to find the L2 minimizer of this equation, right? And we all remember how to do that because some of us have recently taught linear algebra. I had to look it up. No, I'm not sure. This is one of those things burned into my brain at this point in my life. So what is it? It's A star, AA star inverse, right? That's what this is. You do that, oh, AH is just A star inverse, which is just MM inverse, which is the. So under this non-degeneracy assumption in finite dimensions, I could find such a map. Okay, The probabilist in the room may be slightly upset. There's all these questions about adaptivity, so I can do like, you know, martingale calculus on this and all that. You don't need to worry about that. It makes life easier. In finite dimensions, that's nice and easy. I've also made a strategic retreat from worrying about all that today. I just want to give you the ideas. So if you can make sense of this in your setting, you're golden. Whether you use some adjoint tricks, which is what I used in the beginning, or whether you use rough paths, or whether you're in finite dimension and you use, right? So what Maluman did was he actually pulled this matrix M from the tangent space at time M back to the tangent space at time 0, like any good differential geometer would, by using the inverse of the Jacobi flow. And then you evolve it at time 0, and then it's an adapted object, and you can do stochastic calculus on it. The problem is in infinite dimensions, taking the inverse of your linearization is very complicated, right? Unless you're like know exactly you're on the invariant manifold, and you know that you can time invert your flows there, and you know there's lots of reasons why that's complicated, and maybe it's just better not done. This is super important right there, and how I got this, and how this followed from this definition, and how this was my definition of M. I mean, in some sense, that's Hormander's theorem right there. And given that, then I can integrate by parts and get the smoothing estimate that I showed you. Right? Given the smoothing estimate I showed you, I already showed you that once you had this, we can use integration by parts and get that smoothing estimate, right? That gradient estimate. So modulo adaptivity concerns, if you want to use martingale calculus on this, okay? So now, because I want to draw lots of pictures and I want to make sure I didn't go too fast, I'm now going to do the rest on the board. Am I in the right place? Well, just I can use these two. I'll be fine. I may need it. I'm not going to switch mid-lecture. That's irritating.
So if you're in the non-adaptive case like this, connecting invertibility of the value matrix to Hormander's condition is the not obvious piece.
No, it's not connecting. No, okay. So the thing, I don't know what you just asked. I mean,
You said it was Hormander's.
Yeah. Okay. So it's okay. No, even in the adaptive. Okay. So Sam's asking a question. He's right. There's something I haven't shown you yet. So when you normally think about Hormander's condition, what you say is like, okay, I have some x k's, which are my sigma k's dot grad, right? And then I have my nonlinearity in this case, which is kind of my, if you'll let me, I'm just going to call it B. By that, I mean the B that I had before grad this. Yeah. If you'll allow me that abusive notation. Then I start, what does Hormander say? Hormander says, well, you first, so when Sam wrote this in his class, in his lectures, he wrote this. What? I'm writing something wrong? You want the span of this to be the whole space, right? Right? Or you want this to somehow be dense in L2 in our setting, so it's non-degenerate, okay? But another way to write that, which I think is useful, especially this looks super slick, and you're like, yeah. Let me just point out let me just say this. So you could define S0 to be the span of the xk's, okay? Which is just the span of the sigmas that I had before, because these are all constant vector fields, okay? Then you can define Sn plus 1 to be the, I just want to keep writing span. I can't stop it. It's like I'm a little kid who's told a joke, and now I can't stop telling it to everyone. All right, so, oh, and I should also include Y. So I get to have the things I already had. Yeah? All right. So the question is, in a way, the thing I haven't actually explained to you, which I should actually, and I kind of forgot that I need to explain to you, and I think Sam was politely asking me this question. Oh, he messed me up by bringing the adaptability question. Is why does the condition that this eventually, if you go up for big enough n, or in the infinite dimensional case, you actually have to take infinitely many brackets. We actually study this all the way to infinity to prove non-degeneracy for all of L2. How does that relate to these brackets? how does that relate to these brackets? Yeah. Okay, so I hadn't actually planned to talk about that right now, but I'm going to foolishly try to show you off the top of my head. That always goes really well, doesn't it? All right. So somebody comes up to you and says, so what's your role? Your goal is to show that if is you say, okay, let's get the low-hanging fruit. If this is equal to 0, then these are all positive quantities, right? That must imply, for instance, that JST sigma K C is equal to 0 for all S in the interval 0t. Yeah? And you can say almost all S in the interval 0t, but then you can show this is continuous in S. Okay? And if some of you are worried, like, how do you show it's continuous in the initial condition? Is sigma K what I often call, which I'll call J star STC? This is, and what does the adjoint of a linear equation solve? It solves the time reversed version of the linearization with the adjoint of the linear operator. So this is now an equation that takes initial data at time t and flows backwards in time s. So now you just have, and you're like, oh my God, you just took the adjoint of the Laplacian and you're trying to solve the equation. I'm going to lose my, because, you know, right? But you don't have to worry because I'm running it backwards. So the backwards negative heat equation is perfectly wonderful. Okay. So you just prove that this is nice and continuous using just linear theory. Okay. All right. So right away, what did you learn? And then in particular, you can evaluate S at time t, which was the initial condition. And that implies that sigma K C is equal to 0. Yeah. So you've learned right away that it can have no projection onto the directions you're forcing. And now we need to find out whether I was foolish. So what equation did J satisfy, by the way? Satisfied Laplacian. So let's just call it, it satisfied some gradient F at QT times J, and this is C, S, T, C. Yeah. I'm just calling that F, my right-hand side, okay, for a second. Yeah. And now if I differentiate, okay, so there's a couple different ways I can go about doing this. You can actually, so in the work that we did, you actually do this by looking at, so this goes back to a paper I wrote with Etienne Pardue, who's the master of adjoint stuff. So we actually use this time reverse adjoint, okay? You don't actually, at the level of just showing that it's non-degenerate, it's useful to get, or you can, and then there's later papers that Martin wrote and other people where they actually use rough path theory, which I don't think you have, I mean, it depends on what's easier for you, right? It's like when the probabilist says, can't you do that without PDs? And the analyst says, can't you do that without probability, right? So it kind of depends on, except unless you're a stochastic analyst, then they're like, yeah, I can do it two ways. Right? You know, so I always forget this is being recorded. It's like, you know, who said the circus is out of town? All right, so what? One way is better than other, though. Some people have rigid notions of self-identity, you know, and that's fine. All right, so did he respond? No. Okay, so you could sorry, now I'm totally off my game. All right, thanks, Scott. All right, right. All right, so if this is identically 0, what would any sane person do? Differentiate it, right? Right, so that you could differentiate this thing. In particular, if I differentiate this adjoint, so you can actually do this, and I actually intended to not do this way, but now I'm going to. So if I differentiate like this, so now I got that this is identically equal to 0, yeah? And what was this equation? This equation is actually just sigma K. This should be S. This should be T. Right, so I haven't done that. That's correct. So this is adjoint. Because what equation does the adjoint satisfy? It satisfies in S. And so this is like that. And so now I differentiate this, and this is S. Yeah. Okay. And now if I flip it back, if I flip this back, I would get grad F Q S sigma K J S T star. See, yeah. And now if I evaluated S equals T, so now if I take S equals T, I get that this is, and this is actually the next bracket. This is the next bracket. This is F sigma evaluated at QT. Okay, so now I got the next bracket's not zero. And if I keep doing this, I'll keep iterating more and more, and I'll keep getting more of these on, and I'll keep collecting the brackets, okay? And so little by little, I'll learn that C can have no projection onto any of the brackets. And so if they span the space, eventually it's zero. Okay, there's a little subtlety here that I'm working at the end point, and you have to deal with that. So you either have to have this expression uniform at the end point, or you have to play some other games and work for short time and play some games, but you can do games like this, okay? The nice thing about the Maillard matrix is that once it becomes non-degenerate, even on a short time interval, it stays non-degenerate forever. Okay, so that's a small for the cognizance. Just if you're worried about something, dwell on that for a second. All right, so this is how the non-degeneracy comes into the game. All right, so how am I doing on time? How long do I have? A little more than 20 minutes. Okay, so unfortunately, I just lost that. I may abandon that. Okay. Do I jump?
You want forward, backwards?
Do I have to put the thing up there? No, I can't do it. Redemption. There we go. Good job. Thank you so much. Sorry about that, man. All right. All right. So, no second. I'm going to learn. Which one do I press? Gauche. Droite, gauche. Got it. All right. So, So what was the idea then? So through this argument, we could actually prove that this Maillard covariance matrix for the Navier-Stokes equation in infinite dimensions is non-degenerate. And from that, you can deduce that if you project it onto any finite dimensional space, this random variable UT, you take any finite dimensional subset of L2, you project onto it, we can show that that random variable has a density. With a little extra work, you can show that random variable has an everywhere positive density by adding some control theory. That's already cool. With some extra work, I'm not going to show you, you can prove that as a C infinity density. All right, now, but for this argument today, right, I'm talking about ergodicity. Should be there, shut some ferns. All right, so what I want to do though, what do? I only cared about ellipticity on those unstable directions. There's always some finite dimensional subspace, right? So I just need to be able to invert the Maillard matrix on that finite dimensional subspace for any fixed viscosity, no matter how small it is, that is a finite dimensional set. So I just need to be able to have on that set, which is the control, which was the kind of the ellipticity, the effective ellipticity set, right? That I called it before, right? So I just need to be able to invert it on that. And if I can invert it on that, then I'm in business. That's where the project with Martin and I started. All right, so now let me tell you the sketch of the idea. I have what, 15 minutes? Is that correct, Matt?
20 minutes.
Okay. All right. So the idea is the following: is just for simplicity, on each interval of time, so between n and n plus 1, or n plus a half, I guess. Let's just do 1. I'm going to define a regularized Maillard matrix. So I defined the thing as a function of t, but I could have also given you an initial point, right? A time to start on, the time that I'm going to calculate. I could have just restricted that integral from 0 to t, but from the first time, which is n, to a second time, which is n plus 1, okay? And so I'm only thinking about the Maillard matrix on that little block. And so that's only the effect of ellipticity for the noise between time n and n plus 1, yeah? And this beta here is because I'm going to put beta times an identity. So I'm going to use the Tipnikov regularization of this, okay? So I'm going to regularize this matrix, okay? Just by adding a little bit of beta. All right, now I can invert it everywhere in L2 because I've added the identity in L2, yeah? Actually, do I even need the whole time? Because I wasn't actually planning to give all the details. And now I have, now I'm in that horrible situation where I have more time than I thought I did. All right. All right, so what's the idea? You're probably not supposed to say it out loud, are you? All right. Actually, you know, it's going to take me a while. Okay. All right. So I have some high modes and some low modes. I've just projected my solution U, writing it equal to L and H, where this is in this projection that I had before of L2 of the torus, direct sum, right? To that decomposition, right? Yeah. Okay, and that's my L and my H, yeah? And so this is a cartoon, but it's a cartoon of that, all right? So what's the idea? So I've made some perturbation in this initial condition, right? What did I want to do? Does anyone remember at all? What I wanted to do was I had this difference, right? Which was the J of T, which starts at 0 up to C. And I want to compensate for this by making an H, yeah, finding an H, finding a wiggle of my Brownian motion path down here, right? Here's my, find this wiggle here. I get fired for that. All right, so I wanted to find this H so that this rho went to 0, right? Remember back to the proof when I did the uniform ellipticity. What did I do? I killed the low modes exactly and then drove the high modes, and the high modes contracted. Now, what I could have done instead was I could have killed the low modes gradually. So when I did that before, I could have, just to help your intuition, I could transform low modes into whatever equation I want. What's wrong? I could have transformed the low modes into this equation, into actually just, I could have just changed these into this, for instance. I could have gotten rid of all the nonlinear and just changed it into that, yeah? Right, and then I mean, when I mean that, I meant the kind of the rho, the pi like this. And then I would have had the pi of t of the high modes, remember? Remember this, when I had rho was u minus u tilde, yeah? And then I had the full equation here. I had the pi and then all the stuff, yeah? Like that. If I did this, would they actually converge at a finite time? No. They would just converge asymptotically, right? Because the heat equation is going to 0, yeah? But what would happen is this had some pi rho in it, along with some other stuff, yeah? But as this got smaller and smaller, this would contract up to a certain scale, right? It's like solving this equation. What if I told you that I had this equation and that I told you that f of t went to 0? X would also go to 0 over time, right? If this is going to 0 exponentially. If this goes to 0 exponentially, yeah? But what would happen is X would be at a certain scale, and then when F got smaller, then X would become on that smaller scale and keep going, yeah? It would just keep getting smaller and smaller, right? So if this is going to 0 exponentially, yeah? So that's the idea behind this. 10 minutes?
Yeah.
No, I can't, right? I'm trying to make sure you understand, but I can't not leave enough time to then explain, because that will have blown the reason for explaining it, right? All right, so we're gonna do exactly that, right? So on the hashed intervals, thank you. I'm so sorry, I'm a failure. Okay, so on the hashed intervals, IL smaller. These intervals make it smaller by shifting infinitesimally with h, right? And what are we going to set that equal to? We're going to set it by setting an h equal to, what did I do before? I had a star, then I had n inverse, right? On that interval. So n plus 1 inverse. So I don't know if I got them lined up right, but like this times what was kind of at the beginning of time at 0 to time n c, yeah? And so let's see. So this is going, so 2n to 2n plus 1, and then this is 2n plus 1 to 2n plus 1, okay? So on this interval, I'm going to invert that. So what happens is at the beginning, what arrives at each interval is the perturbation that I have left, right, to kill off. And over this interval, I'm going to do what I did before, which is kill out the low modes. Right now, the point is that this beta here, if beta is very small, this is essentially a true inverse on the low modes. On any finite dimensional subset of this, which is non-degenerate, as I make beta small enough, it'll be a true inverse on that projection. So on that on that little chunk of low modes, this is a good inverse. So I'm going to take energy out of the low modes. And then you show that it doesn't mess up the high modes too much, because at worst, it's just got the inverse has a 1 over beta times it. So it messes up a little bit, but not too much. Okay, you can show through some other estimates, okay? Then what happens? So here I'm kind of thinking about this. So there was a big perturbation here. And now at the end of this interval, this is smaller, as you can tell, right? Smaller. And the high mode perturbation, whatever it was, it's maybe a little worse, but it's not much bigger, okay? And now what happens? Because the low modes are now smaller, the perturbation there, the high modes actually contract down because they have to get at the same scale as the low modes, right? These are my low mode difference. And now the high modes, which are the x, have to contract some to get on the same scale. And now you keep iterating this. You keep iterating this. You take out some difference in the low modes, right? Okay. Now there's some subtleties in here, right? I mean, if you think about this matrix M, and you branch it into low, low interactions and high, high interactions. And whenever I teach linear algebra, I have to write on my hand the rows or the columns come. So I'm going to guess that this is low, high, and this is high, low, but I really don't know. Okay, so you'll tell me in a second. All right, I think this is high, low, right? Anyway, it doesn't matter. So you need some control. The fact that this doesn't mess things up too bad had to do with knowing that stuff, this off diagonal information, which we have control of, okay? That's a subtle point. But this is the basic iteration. So this is a paper with Martin Hare. And what it does, and then there's a follow-up which talks about it in a more general setting. And the idea is that we iterate, removing low mode, high mode, low mode, high mode, low mode, high mode, low mode, high mode, okay? And when we take it out with the low mode, we take it out the variation, right? We're trying to drive rho for the trees. We're trying to drive, where was the definition of rho? Ah, right, thank you. We're trying to drive rho to 0 by changing h. So on these intervals, the hashed ones, we choose h so that it takes something out. And we've made then rho smaller. Then on the next interval, the natural dynamics on rho drives it to 0 a little bit more because it's contracting now. So this is slightly misleading the way I've written this, but it's not so misleading. That's actually not bad. I mean, because you can kind of telescope this out, right? You can write this as a product of a whole bunch of j's, like j's over intervals, right? K plus 1, right? Okay, and then a sum. Okay, no. But yeah, just like this. So you could write a whole product, a time ordered product. And so you can kind of factor them out. And so they keep kind of acting on so what you do is you end up writing a recursion, rho n, and then there's some operator, which is random, that depends on rho n minus 1. Once you've gone through one full cycle of this. And you show that in expectation, this thing contracts. And then once you have that in expectation, that thing contracts, we actually need a little bit more. We need some of these constants and these coefficients to have control over them. So we bound them all with Lyapunov functions so that we can get kind of nice exponential martingale inequalities on. And then we control all that. So there's a lot of junk here, not junk, it's important stuff. It took me a long time to, put all the pieces together. So, but yeah, so I mean, that's the basic idea. Okay, and so it really is this. Let me just tell the whole story one more time. Now that you've heard the whole story, I can tell the whole story like we're sitting someplace having a coffee. Okay, so here's the idea. All of these equations that are dominated by the Laplacian, their leading order symbol is dissipative, and the nonlinearity messes things up, but it only messes it up on some finite dimensional, typically, energetically, where the size of that depends on the energetics of the problem. Outside of that space, I have contractive dynamics. If I were to make the low modes contract to each other by changing the noise, then the high modes would contract. That's this idea of Fourier-Spadis. When I have enough noise on all the low modes, I can get rid of them, and all's good. When I don't have enough noise, when I need to use hypoellipticity, I can then iterate these through the system, through the nonlinearity, to make this Magellan matrix non-degenerate, right? I can't do it infinitesimally like I could before, right? Before, when I had the noise everywhere, I could just infinitesimally correct for it. But I can't now. I have to wait a kind of a macroscopic or at least a mesoscopic amount of time, right? That's that singularity at time 0 that Sam was worrying about at some point, right? So I have to then go out time 1, and then I correct using the Magellan matrix to pull the noise out. There's some subtlety here about the fact that this is not adapted, but that's not, I don't think it's good for this room. Okay, to worry about that. And then, and you know, you could do it with other ideas too, right? You could do it with rough paths, you could, and I've thought about ways maybe to do it in. Then you let the high mode dynamics pull it in. Then it gets, they're both smaller. Then you make the low modes smaller. And then the high modes get pulled in and then low modes, and you just keep iterating. Okay, and then asymptotically you've proven that this rho goes to 0 for some h. And then you have to show that the h you generated summable, had a finite L2 norm all the way out to plus infinity, so that you didn't change the measure. And that's not reasonable. That is reasonable. That is reasonable because my h, right? My h was defined by that. So it scales, it's a linear operator applied to this. So if this is converging exponentially, then I would expect the h's size to decrease exponentially also. So once you prove that this is going to 0 exponentially, then you deduce that this is also going to 0 exponentially. So it's summable. How do I do it?
You have 3 minutes if you want it.
I do have one more thing I could say. This discussion, to a large extent because of the audience, I chose to give this in a very kind of Markovian PD looking way, like that looked like estimates you see in PD land. I could have also used a Fourier-Spadis reduction, which says if you know the infinite past of the low modes, you can reconstruct the high modes with some functional at time t of the low modes from time minus infinity to time t, right? You can reconstruct it. And so then you can close this equation as some equation on just the low modes at time t as some functional of the low modes from minus infinity to time t plus some noise. Turn this into a finite dimensional SD with infinite memory. Do all this thing again. And now if you're a stat mech person, you say, oh, I have a finite dimensional spin system where the spins are finite dimensional and I'm in one dimension, which is time. There are no phase transitions as long as things decorrelate quickly. And that gives me unique ergodicity also. All right, this also tells you that all the ideas I presented to you in various ways, many of them can be connected to delay differential equations. And the problems that I talked about, and this is my last point, the difficulties that I talked about in proving that if you have, so let's not even make it infinite. Let's say you have some function like this, where this just depends on t and up to t minus 1. So it's a little delay differential equation. It just looks a little bit in the past, right? And that's a Markov set kernel then, where I give it a little amount of time minus 1 to 0. And then I kind of have a dl tilde, which is a little chunk from 0 to 1, right? So that's a Markov process on little chunks of length 1, right? And so a perfectly great, well, what if I make this now depend on, let this now be multiplicative like this. So it just depends on the value at time t. I claim that it's pretty obvious, in fact, that this would be singular if I take another L tilde I can't call it L tilde. Let's call it K. My next paths are K and K tilde, dk tilde. These two Markov kernels, if L on this little interval is not equal to K on this interval, then these two things are singular. Are singular. Not equal, thank you. Yeah, if they're not equal, then it's singular. A little bit of stochastic calculus, you can see that instantly. Because what's happening here is if I'm on a little interval -1, 0, and now I'm looking at this is my L and this is my DL tilde, right? My little futures. Here, all the paths right here have a quadratic variation, which is determined by this 0.1 unit in the past. And if these two things don't equal somewhere, then the infinitesimal quadratic variation is different at those 2 points. And quadratic variation is an almost sure property of a path. And so those paths are therefore singular. They don't agree. Just like if you look on path space, Brownian motion and 2 Brownian motion are singular on path space for the same reason. And so all of these ideas were actually very useful also in proving ergodic theorems for delayed differential equations with multiplicative noise. Okay, so these all come in there in the same way. So I just wanted to kind of show you that this is really a discussion about what happens for a certain family of infinite dimensional Markov processes. And what happens when you all of a sudden start doing Markov processes on infinite dimensions. So these might be useful in even other places. All right. The office is down the hall from me. Isabel first. You can go next.
Yeah, just about your matrix on the floor.
My matrix on the floor.
Yeah. So could you just give a small idea when you have high modes, I guess that goes away because of the energy estimate, maybe. So you're not worried about
You
that?
mean, why does it go away when in this iteration scheme?
Why do the high modes decay?
Because, well, they don't get messed up very much.
Okay, but still, I mean,
Because I have some bounds on them when I do this inversion. But then the reason they decay is because I have the Laplacian acting there, and they're high modes.
but the time is very short, right? But
Yeah, but it's order 1.
I mean, that's not a problem. The low are not EL. The low modes.
The
you're
low modes
saying
are not a
don't
problem.
care.
That's you have to prove. We have enough estimates. We have estimates on this whole thing and how it's not degenerate as an object on the whole operator. So we get information about the off diagonal parts automatically.
Okay, and the high, it's the energy, right?
Yeah, the high, right? We have a stupid bound just from this. I mean, the thing is, when you make the thing big enough, you get so much killing from the Laplacian, right? You get, I mean, I get it killing faster. The NAC, you say it's a short time, yeah, but for the 1000th mode, 1 unit of time is a long time. It's a long time, right? Right, because it's decaying like k squared, right? So it's decaying exponentially, but the rate constant is growing quadratically. Directly divided, maybe linearly, because you should divide by the area of the shell.
Mine, I think I'm too confused to ask a question.
No, ask.
Oh, yeah.
I'm sorry, I feel bad now.
Okay. Oh no. Wait. So like in finite dimensions, like
Yeah.
with the Lie brackets, you have like the noise is like if you only force like a couple of dimensions with the noise, it'll like shuffle through the nonlinear frame.
Yep.
But then like in small times, you kind of get this like weakening effect
Yep.
on the noise where it's like less strong.
Yep.
So like, was this kind of just a way of like dealing with that and
Well, so the problem is, so like, when I first thought about this, and stop, are you listening? When I first thought about this,
Yes.
I really wanted to control the asymptotics of that brackets going scale to scale to scale to scale, right?
Yeah.
But I couldn't, at the time, the point is that in this case, we have this cutoff. The Laplacian gives a cutoff. So we can kind of stop it. We can stop at some scale, right? So I don't have to understand it all the way out to all scales.
Okay.
And that's the point.
Yeah.
And so I'm reduced back to the case which is easy, which is just the invertibility with the control of the off block elements of invertibility on a finite dimensional space.
Okay.
Never doing probability in anything more than a finite dimensional space, right? And that's also why that representation I just drove here might be illuminating to you, because here this L is always finite dimensional, so it has infinite memory, but it's always the probability is happening on finite dimensional chunks.
Like just making sure, like the rho t going to 0, that shows like non-dependence on initial conditions somehow for an ergodicity.
Yeah, so, and what it lets
Okay.
you build actually, so I didn't talk about this. And I guess I could next time if people want me to, but I was gonna talk about something different. Maybe I'll start off with this, maybe. It lets you build a coupling locally.
Okay.
Just that gradient estimate lets you say that the following is true. Just say it in hands, and if I want to, next time I'll say it more carefully. Conditioned on staying near a solution, you can actually show that the solution goes to 0 with positive probability. Or actually conditioned on staying nearby, it goes to 0 in expectation.
Time for one more question.
Oh, just a question. This, when you have the drift with the past history in that,
Yeah.
do you assume some kind of contraction there?
Distance of measures?
Well,
I mean,
in
I'm
general.
assuming that you have one. I'm proving that there's at most one.
But then you don't need to assume your drift to have some.
You have
contraction
to, yes, because you have to
out
prove something, you have to prove the following thing.
Yeah.
So Shumei, what you have to prove. Okay, okay, in words, you have to prove that if the histories are close to each other, the measure on the next path, on the next chunk is close in Wasserstein distance.
it. Right, so it's-
Okay, or you sometimes you can do it even in total variation, okay? So you have to kind of have a bootstrap thing. So you're saying if the past are close in some exponentially weighted norm, right? That cares about the near present more than the far past, right? Then you can show if as that gets closer and closer, the next block gets closer, and then you can prove essentially kind of a cascading coupling. But once you're close enough, the next ones are closer, and then the next ones are closer, the next ones are closer. Yeah, you have to have some
contraction.
information, right?
I would like to see a reference, please.
Let's thank Jonathan one more time.
All right, I want to start clapping.